Air circulation and boundary layer. This presentation was developed by Dr. Margaret McMahon from the Ohio State University and Dr. Cherry Kubota from the University of Arizona. So the content of this presentation includes air circulation with regard to positive and negative aspects in greenhouse, and information regarding what is boundary layer, plant response to reduced boundary layer resistance, and application of boundary layer understanding in greenhouse. And example we are talking about is a tip burn control for lettuce production in greenhouse. So air circulation inside the greenhouse is recommended for improved spatial uniformity in temperature. So particularly air circulation is done using horizontal airflow fans during the time we are heating the greenhouse. Air circulation and the air current speed are important factors affecting plant gas exchange through boundary layer. Gas exchange is including transpiration, which is exchange of water vapor, and photosynthesis, which is exchange of CO2 and oxygen. Boundary layer is explained in the following slides. So what is leaf boundary layer? Leaf boundary layer is basically the thin layer of aerial zone surrounding a leaf due to the reduced air movement inside the layer relative to the bulk air outside the layer. This reduced air movement was result of friction between the leaf surface and moving surrounding air and of the viscous forces within the air. And the layer actually acts as a buffer between air spaces in the leaf and bulk air. And then also, most importantly, air circulation, which is wind or air current around the leaf, reduces the thickness of layer. Again, this layer is a buffer for the movement of gas such as CO2 or moisture, and then also the heat. So this diagram is showing sort of conceptual presence of boundary layer separating from bulk air. Those are the stomatal opening. That is the entrance of gas exchange. Often the microclimate within the boundary layer is very different from bulk air. In terms of CO2, boundary layer CO2 concentration is lower than bulk air when plants are doing actively photosynthesizing. And moisture concentration within the boundary layer is also higher than bulk air when plants are transpiring, releasing moisture from stomatal opening. And actual development of boundary layer is not uniform. It's depending on the size of the leaf, and then also depending on the air circulation around the leaf, and depending on the surface structure of the leaf. So this is another drawing to show how boundary layer might be developed over the surface. The boundary layer is created upper surface of the leaf and then also lower surface of the leaf. And then this is depicting in a way that, windward boundary layer is much thinner than leeward boundary layer, which is thicker. And then this thickness of boundary layer is directly determining the size of the buffer capacity, in another word, resistance to the gas exchange, and then also heat exchange. So this is another example of boundary layer development over flat surface. And this is a case of laminar flow, which is the simplest case to understand the boundary layer. So laminar flow, by definition, is equally distributed wind speed across the vertical profile. And then over the flat plate, because of the friction, because of the viscosity of the air, from the certain height, the wind velocity is going to be reduced and then reaching zero at the surface level. So this layer showing reduction of wind velocity is called boundary layer. And then the thickness is determining the resistance in terms of gas exchange from bulk air into the boundary layer. Because the speed of air movement is reduced, therefore the energy to carry the materials a mass to the next layer is reduced compared to the bulk air layer. So that's why thickness is directly determining boundary layer resistance. And then another important thing is windward is almost none regarding boundary layer development, and then gradually increase as you go away farther from the windward. So the leeward is always much thicker in terms of boundary layer thickness, in terms of boundary layer resistance for the gas exchange and heat exchange. So that means the size of the plate is affecting boundary layer thickness and boundary layer resistance. So this one is a theoretical relationship between boundary layer resistance or thickness and velocity. So this is bulk air velocity, so above the boundary layer. And also another factor included in this chart, which is the leaf width, so the size of the leaf. As I showed you in the previous slide, the distance from the windward to the current location affects the boundary layer thickness of that location of the plane. And then you can interpret that information as that the size of the leaf would affect boundary layer or average boundary layer resistance or boundary layer thickness, because the larger the leaf regard to the the direction of the wind flow, then you have thicker boundary layer develops. So that's why you have 10 centimeter width of leaf, 5 centimeter and 1 centimeter, and then thicker the wider the leaf size, then you have greater resistance at the given air velocity. And then if you have higher velocity, and that means you can reduce the boundary layer thickness and therefore resistance. So the greater the leaf is, or the greater the leaf area is, or the smaller the air velocity is, then you have much bigger boundary layer resistance. And then also the surface structure of the leaf affects the friction, therefore the thickness of boundary layer. So leaves that have dense trichomes, the hairy leaves like this, have definitely thicker boundary layers, therefore more resistant to air movement than smooth leaves. And then also something like that, crinkled leaves are expected to have thicker boundary layers compared to smooth leaves. So those are additional factors coming from the plant, in addition to, the leaf size. Boundary layer resistance is depicted in this diagram as one of the important resistance limiting the gas exchange, photosynthesis, and transpiration. And then this resistance is increased when limited wind velocity around the leaf. And there is a good amount of air circulation or wind velocity, then you have minimum boundary layer, therefore gas exchange is enhanced. So this chart is showing actual measured value of net photosynthetic rate and transpiration rate of a plant leaf as affected by air current speed. And then, as you can see, by increasing air current speed up to 0.5 meter per second or so, then you can actually increase the photosynthetic rate and transpiration rate compared to zero air current speed situation. So to give a perspective, the greenhouse air current speed could be as low as zero point 0.1 or less meter per second. So creating some level of air circulation around the leaves, around the plants, could be a strategy to increase the net photosynthetic rate, water uptake, nutrient uptake, therefore potentially maximize the productivity of the plants. The air current speed beyond zero point 0.5 meter per second doesn't seem to be beneficial, maybe rather negatively influence the plants through mechanical stress or damaging the leaves. One of the application we are aware of based on the understanding of boundary layer affected by air current speed is vertical airflow fans, typically installed in a hydroponic lettuce greenhouse. This is a picture taken at Cornell University, Ithaca, New York, and that is, of course, the lettuce production greenhouse. So the lettuce production, growers want to enhance the growth, but the dilemma is that when plants are exhibiting very fast growth, typically tip burn occurs. So the incident of tip burn is associated with plant growth rate. So this is a problematic issue, and traditionally the growers had to reduce the growth rate of the plants either by lowering temperature or giving up CO2 enrichment or reducing the light intensity to slow down so that tip burn doesn't show up. However, a scientist discovered that air movement around the plants actually helps to mitigate the tip burn. So tip burn shows up around the shoot tip, and then this is the zone having very stagnant air. So that means very thick boundary layer. And then by providing vertical air flow hitting that area by installing fans like this, effectively remove the tip burn because boundary layer is reduced by air circulation around the shoot tip, and then that reduced boundary layer would enhance gas exchange, including transpiration rate. And then if you know tip burn, which is calcium deficiency, and calcium is transported through the mass flow, so the transpiration is the key for bringing calcium from the root zone to the shoot tip, growing to shoot tip. And therefore, reducing the boundary layer resistance would enhance the transpiration rate around the shoot tip, and that completely or almost completely mitigate the incident of lettuce tip burn. So that's why you see this kind of vertical airflow fans installed in hydroponic lettuce greenhouse. For more information about boundary layer, I have few recommendations. Number one is a YouTube video, Fluid Mechanics, which is a great visualization, which is an old educational movie, but I think this helps you to understand what is boundary layer and how the wind speed affect the boundary layer, or the distance from the windward affects the boundary layer thickness. And then the second one is Plant Growth Chamber Handbook, Chapter 6, Air Movement. That also helps you to understand what is boundary layer. And then the last one is the Hydroponic Lettuce Handbook, in which you can find the description of vertical airflow fan to mitigate tip burn of the lettuce. Thank you very much for listening.